We continue our description of molecular compounds by looking at geometry of molecules. We will look mainly at molecules of p block, that is of groups 3, 4, 5, 6, 7, and 8. This theory doesn't work well for transition metal elements and is almost useless for ionic compounds. It is related to name of our good Canadian neighbor Ronald Gillespie, who is professor at McMaster next to us. You may want to look. The theory is named after valence shell electron pair repulsion. As I told you, it's also related to Gillespie-Nyholm names. Later on it was slightly improved to become ligand close packing theory, LCP theory, almost the same as the previous. The main idea is that repulsions between electrons determine the geometry around the central atom. Just using plain logic, you have electrons being negative. If they do not form a chemical bond, the only interaction between electrons would be electrostatic repulsion. In general, electrons want to be as far as it is possible from each other. As a result, chemical bonds are located as far as it is possible from each other. Basic electron arrangement are very few. First, if you have two electron domains, so areas where electrons are located, it can be chemical bond or it can be lone pair, you'll have linear arrangement. 2 points are as far as it possible from each other if they are at opposite sides of the central atom. Same logic shows that if there are 3 domains, they are arranged as flat trigonal triangle around the central atom. Angles here are identical and are 120 degrees. If we have 4 electron domains, the same arrangement will give us tetrahedron. Just let's look. Tetrahedral is very common arrangement. It can be drawn in different way, like this. In mathematics, it will look like this. In chemistry, we often draw it using dotted bond for backwards directed and solid for forward directed. That's an example of tetrahedral CH4 molecule. Now, if we have 5 electron domains, the best arrangement will be trigonal bipyramidal. So you have triangle and 2 points above and below the main. If you have 6 domains, you have octahedral arrangement. What about numbers above 6? They exist, but they are relatively rare, and I will not go after them in this class. Octahedral can be described like this. All angles are 90 degrees. In mathematics, they draw it in this fashion. That's an example of octahedral molecule. Two fluorines directed towards back, two fluorines in front, and sulfur is in the center, SF6 molecule. Now, if a domain is between two atoms, so it's chemical bond, covalent chemical bond, we name it bonding domain. If you have a lone pair or sometimes a single unpaired electron, it's non-bonding domain. Which of them will occupy larger space? It's a little bit counterintuitive, but non-bonding domains are larger. Why? Because there is no other attractive center. The second nucleus is attractive center for our electrons. If there is no other attractive center, electrons are trying to be as far as it is possible from each other, and they are occupying larger space. So non-bonding domains, that is lone pairs mainly, are larger than bonding domains. Now let's look at geometries for cases with bonding and non-bonding domains. With two domains, it's easy. You still have straight line. With three domains, you have two options. If we have all three domains bonding, you have a triangle. Now, if you have one lone pair here, you'll have a bent molecule, and this angle usually is smaller than 120. Why? Because this domain occupies larger space than these two chemical bonds. In case of tetrahedral environment, we have three cases. One of them is four chemical bonds around central atoms. Example is methane, CH4. All angles are ideal tetrahedral, and they are 109.5 degrees. If one of domains is a lone pair, you have trigonal pyramid shape arrangement of atoms. This is not a flat molecule. It's very important. Angles are slightly smaller than 109 because of larger repulsion from the lone pair. If you have two lone pairs, you again have bent molecule, and larger repulsion from two lone pairs will give you even smaller angles, so not 109, something like 105. This is the case of water molecule. For case of 6 domains, we have several possibilities. One of them is all bonding, that's usual octahedral. Now we have one lone pair here, and our molecule will be square pyramid. Because of larger repulsion from here, all four atoms in a plane will be slightly above the position of the central atom, something counterintuitive. If you have two non-bonding domains, two lone pairs, they will sit at two opposite positions. The reason is very simple, because they repel each other so strongly. The remaining atoms will be ideal square planar. The other possibilities, I'll skip it in this class. So let's look at some simple examples. We have methane, 4 bonds, tetrahedral environment. We have ammonia, 1 lone pair and 3 bonds. We have trigonal pyramid. And we have water, 2 lone pairs. We have band structure.